We have our seminar speaker coming all the way from the north wing of our building. Dr. Amanda Lietz is an assistant professor in our local department at NC State, and the leader of the Computational Plasma Science group began just this fall. Her group focuses on developing and using plasma simulation tools for low temperature plasmas. Low temperature plasmas are critical to many current and potential future technologies. Of particular interest to the group are semiconductor processing for computer chip production, biomedical treatments, and electrification of the chemical industry to reduce fossil fuel consumption. Dr. Lietz has a PhD in nuclear engineering and radiological sciences from the University of Michigan and a BS in nuclear plasma and radiological engineering from the University of Illinois at Urbana. Before joining NC State, she was a postdoc at India National Laboratory in the Applied Optical and Plasma Sciences Department. She has been named an emerging leader by the Journal of Physics, The Applied Physics, and received the Richard and Eleanor Towner Prize for outstanding PhD research. With that, I'd like to say thank you very much for your this great seminar we're about to hear, and thanks to everybody.
Thank you very much for the introduction. As Dr. Vitaler said, today I'll be talking about computational modeling of low temperature plasmas for problems large and small. So a brief agenda. I know some of you work in the plasma area and some of you don't. So I wanted to give some background on what is a low temperature plasma and in general, what are they used for? Why are we interested in them? And also, what are the approaches that we use to model these systems? And then I'll delve into some more specific research studies and results from modeling across areas, including plasma medicine and mass spectrometry as well. But before that, just briefly, my group is Comps Group, Computational and Plasma Science Group. We just started this August, and it's myself and 2 PhD students. And we focus on pushing towards kind of modeling real conditions. So that means trying to address reactor scale, so plasma reactor scale, and more complex chemistries, as well as including things like surface reactions, surface interactions. Tackling these problems involves using existing tools and developing new tools. So what is a plasma? Plasma is often called the fourth state of matter, but we like to refer to it as the first state of matter because most of the matter in the universe is actually a plasma. So you've probably seen this before. I think in the hallway out there is a copy of it. But this just demonstrates the range and parameter space that plasmas can cover. So we've got at least 6 orders of magnitude in temperature and about 20 orders of magnitude in density. So it's a huge range of conditions from the core of stars out to very diffuse plasmas in space. High energy density plasmas for fusion are somewhere up here, and we're focused more in this region. Now, low temperature plasmas is a subset of that. And so usually low temperature plasmas are plasmas with gas temperatures much less than what would be needed to cause thermal ionization. They're mostly generated with electric fields, though not always. But if you take a pair of electrodes, you apply a voltage across them, you get an electric field. And then if the electric field is high enough and you have an initial electron, the initial electron is accelerated in the field and then can cause electron impact ionization, which is this process here. And you get an electron and ion, and the avalanche continues until you get breakdown and a plasma develops. They're used in all kinds of things, from fluorescent light bulbs, so you may see them in neon signs, but also are very useful in manufacturing for activating surfaces, and especially for processing materials for producing computer chips. So this is a very high-level, simplified description of why electrons in plasmas are more energetic than ions. So in order to have a plasma, you need some energy in the system to be high enough to cause an ionization. So in a thermal plasma, this could be the gas temperature. But when you apply an electric field, very simply, F equals ma on electrons and ions, and we can integrate calculated velocity, and in an oversimplification, we can say that the temperature is equal to the average kinetic energy, And just that this temperature in a fixed field with no collisions or anything fancy happening, the temperature goes like 1 over the mass. And that means that because electrons are light, they're accelerated more rapidly by an electric field. And we get electron temperatures that are much, much higher than ion temperatures. And in low temperature plasmas, often the conditions are very weakly ionized. So even parts per million or parts per billion ionization is enough that the plasma dynamics can be dominant. So once we have hot electrons, or energetic electrons, all kinds of different things can happen. First is the most obvious, an elastic collision. So just some energy transfer to gas heating. And then very importantly, electron impact ionization. If electrons are in the few eV to 20, 25 eV range, this can start to happen. And this is what sustains the plasma. That's why this is typically a very important reaction. But we can also have a lot of other reactions like electron impact excitation, producing excited states, vibrational excitation, if you have molecules. If you have molecules, you can also have dissociation, dissociative ionization. If any of the molecules are electronegative, you start to get attachment as well as dissociative attachment. There can also be superelastic collisions. Once you get excited states, that excited energy can transfer back to kinetic energy of the electrons. So this is just the electron impact reaction. But once we have non-equilibrium chemistry, there's other things we have to consider. So if you have excited states, radiative relaxation emits UV photons. Penning ionization can occur if the energy of the excited states is higher than the ionization energy of something else in the system. Then once we have UV photons, we have to consider photoionization, photodissociation, and photoelectron emission from surfaces, as well as some charge exchange reactions, either symmetric charge exchange reactions, which can result in hot neutrals, or asymmetric charge exchange. And with this combination of electrons being accelerated in electric fields and then losing energy to all of these elastic and inelastic processes, we very often get non-Maxwellian electron energy distributions. So this is a calculation of some electron energy distributions in an argon plasma. And in these units, Maxwellian distribution is linear. If we have a very low ionization fraction, it diverges significantly from linear. And then as the ionization fraction increases, there's more electron-electron collisions, and it starts to approach Maxwellian. But this non-Maxwellian distribution means that we have to use cross sections instead of rates for electron impact reactions. And so that means that we end up usually solving Boltzmann's equation with a very specific set of assumptions for electrons in order to calculate the electron energy distribution. So that's often called a two-term spherical harmonic expansion, where we just solve the electron energy distribution in 0D in steady state. And that way we can look up the reaction rates as a function of electron temperature, even for non-Maxwellian distributions. But sometimes that's not enough. And we have to use fully kinetic approaches where we don't assume as much about the distribution. And usually that's a Monte Carlo approach. So one common application area of plasmas is plasma medicine. So atmospheric pressure plasmas have been used for improving wound healing, selectively killing cancer cells. They've been shown to kill bacteria and heal wounds or heal lesions. And this is mostly attributed to reactive oxygen and nitrogen species and requires low gas temperatures. You don't want to burn people while you're treating them. And this means mostly using dielectric barrier discharges, which is the type of plasma source shown here, or atmospheric pressure plasma jets, which both keep the temperature very low. In these cases, the surface to be treated is usually covered in a thin layer of liquid. So plasma liquid interactions are important too. Another area of interest is water treatment. So plasmas have been used for a long time to create ozone since the 1800s. And this can be used for water treatment. This is more of a conventional established method, but now people are more looking into direct treatment of water by plasma. And this is especially targeting removing some very difficult to remove chemicals. For example, PFAS, which is a class of chemicals that are often called forever chemicals because they're so difficult to destroy when they're in much of our drinking water. And the challenges in this area are for things to be very scalable, cheap, fast, because they have to be applied to a large quantity of water. And I mentioned dielectric barrier discharges. This is one type of plasma source that keeps the gas temperature low. This is two electrodes. In this case, they're both covered in dielectrics, and a sinusoidal voltage is applied across them. And if the field is high enough, we get a breakdown. That breakdown charges up these dielectric surfaces until the field is no longer high enough and it shuts off the discharge. And then when the voltage goes to the opposite polarity, the field goes in the other direction, and that surface charge leads to field enhancement, and it breaks down in the other direction. And this continues with every sinusoidal cycle. In these discharges, typically they last about a nanosecond or about tens of nanoseconds and repeat on the order of milliseconds. So another application area of low temperature plasmas is in semiconductor processing. And in order to understand this, got to understand a little bit about plasma sheets. So when a plasma contacts the surface, a sheet develops, and this is because the electrons are light and hot, so they diffuse out faster. And then the plasma becomes positive, and this potential barrier develops that retains electrons in the plasma and inadvertently accelerates ions out of the plasma. And so that means that the ions end up directed toward any surfaces. And this can result, or this can allow for anisotropic etching. So you sort of have tiny beams of ions bombarding the surface at all times. And if you want to etch a channel that looks something like this, you want to etch it straight down, then those ions are very useful for getting that directionality. And usually they're combined with some kind of reactive neutrals as well to enable etching. The plasmas are also used for thin film deposition, which is once you etch this trench, you've got to fill it in with something. And in modern computer chips, features are getting down to very small sizes. This is a recent release from Intel where some of the features are 30 nanometers at the bottom. And so we're really approaching atomic scales. And so there's new types of processes that are, and new challenges that are coming up with atomic layer etching and atomic layer deposition, which both use plasmas as well. And so just to kind of point out some other areas where plasmas have applications, I just went to the National Academy of Engineering and each of their grand challenges. And many of them, not all of them, involve low temperature plasmas or could be influenced by low temperature plasmas. So making solar energy more economical. So plasmas are used for deposition of thin films in photovoltaics now, but also can be used to generate nanostructures, which could develop new photovoltaic technologies. Engineering better medicines. We talked about plasma medicine, but also plasmas can be used for nanoparticle production for drug delivery and providing access to clean water, destroying PFAS, generating ozone. And also providing energy from fusion. This one's more obvious. Fusion technologies are all plasma-based, but there can be some low temperature plasmas that occur near the walls or in some auxiliary technology. Managing the nitrogen cycle is a popular topic in low temperature plasmas right now. Using plasmas to fix nitrogen and produce ammonia or nitrates as fertilizer. Carbon sequestration, going beyond carbon capture and storage into carbon capture and utilization. Plasmas can be used to enact this endothermic chemistry and store energy is chemical fuels. And engineering the tools of scientific discovery. So plasmas are used in mass spectrometers, in plasma thrusters for space application, and in quantum computing. And then, of course, microchips influence everything. So now getting into how we computationally model these plasma systems. I've got here kind of a spectrum from a very simple 0D steady state Boltzmann solver up to a fully kinetic simulation. And as we move from left to right, we're removing some of the assumptions and getting to more complicated models. So the Boltzmann solver is not really a full plasma simulation. When I say Boltzmann solver, we really mean a very specific kind with a steady state and 0D approximation. And this just gives us electron energy distributions. And then moving to a 0D model, we approximate the plasma as a well-stirred reactor. And this is great for very complicated reaction mechanisms where you don't really know what's important. And then fluid models, usually a multi-fluid approach. This is very common. And increasing complexity, we can move to hybrid models, which doesn't really have a specific definition. This is just anything between fluid and kinetic. It could mean fluid ions with kinetic electrons, or electrons that have a fluid component and a kinetic component. And then kinetic simulations usually are Monte Carlo simulations. There are some direct kinetic methods that aren't particle-based, but mostly it is particle-based simulations with Monte Carlo collisions. And those don't make any assumptions about electron energy distributions or ion energy distributions. And to give you a sense of where this gets you, the first two are kind of lightweight models that could be run on a laptop, and the more complicated 0D models, you start wanting to offload that. And then fluid models, you really start wanting to parallelize, and moving into hybrid models, depending on the hybrid model, and particle models. Really, to solve relevant problems, you need massive parallelization, and things are moving into GPUs as well. And the timescales, even with this level of parallelization, the timescales that you can expect to achieve in global models, we can get to minutes, but moving into the more complicated models, we're often very limited. Milliseconds is typical for a fluid model, but depending on the problem, you could really be limited to nanoseconds in 1D for a fully kinetic simulation. So now I want to go into some specific, more specific research results. This is on admixtures in atmospheric pressure plasma jets. So this is a common plasma source for plasma medicine, where helium or argon usually flows through a dielectric tube, and a voltage is applied across electrodes that are in or on the tube. And the plasma begins in the tube and then extends out where it comes in contact with humid air and can produce more complicated chemistry. And a lot of times admixtures are flowed through the tube to get a better control or produce selectively more reactive oxygen species. And our objective here was to computationally investigate some of the initial and longer timescale production of reactive species when admixtures are present. And so this uses a 2D fluid model of non-PDP-SEM, where first we run the fluid calculation to a steady state. So this is a cylindrically symmetric discharge, or a cylindrically symmetric domain, and run the fluid to steady state and then apply a high voltage pulse with a 170 nanosecond pulse with a 20 nanosecond rise time. And we include parts per million level of impurities in the helium flow. So this is 99.99% pure helium. And even these small levels of impurities, we'll see, can have some influence. But once we include humid air, we have to include at least 51 species and 717 reactions in this mechanism. Applying a voltage, we get an ionization wave that propagates. So the plasma starts near the powered electrode and then moves along the tube and charges the surface of the dielectric tube as it moves. And most of the ionization, this plot is of electron impact ionization rate. the volumetric rate. Most of the ionization occurs at the front of the ionization wave, and it moves up in time and then converges at following the interface of the helium and the humid air that's diffusing into it. And then at the end of the pulse, we get an electron density. And even though there's only parts per million level of air species in the tube, that's where a lot of the reactive species are generated, with the exception of single delta oxygen here. But most of these species are coming from in the tube initially. And then at later time scales, we moved hundreds of microseconds, the flow pushes these reactive species out and they mix with the surrounding humid air and form more complicated and more stable reactive species. And we can look into the mechanism and highlight some of the most important reactions that we can trace these species back to. So now if we add intentional admixtures more at the 0.1% level, for the first 0.1%, we see the most effect in the reactive species that are generated. This is on a log scale. But also the ionization wave changes a little bit and the reaction and, excuse me, the energy deposited increases as well as we add water vapor to the mixture. Importantly, the excited state nitrogen decreases significantly from because there is some competition with charge exchange with water vapor. And I only showed in detail the water vapor. We also added oxygen. And one of the key findings here was that without an intentional admixture, most of the reactive species production is due to the impurities, which you probably don't have control over in the lab. So in this case, 80 to 100% of a lot of these relevant reactive species come from parts per million impurities. But when we add an intentional admixture of 0.5%, either water vapor or oxygen, we can reduce the role or the sensitivity to impurities that you might not have control over, especially for the case of water vapor, because you're getting reactive species generated that include hydrogen plus oxygen. Now we're going to talk about plasma-induced flow instabilities in atmospheric pressure plasma jets. So this is something that's been observed in many cases where a plasma is on or a plasma is off, you get a nice laminar flow, and you turn on the plasma and the flow becomes unstable. The mechanism really hasn't been proven though. And a lot of studies have speculated it could be gas heating, it could be an ion wind component or a buoyancy of the helium. But we know that disturbances in the flow can affect the way reactive species are produced and the way plasma propagates. So it is an important question to understand. So again, we use a 2D fluid model to look at this question. We allow the fluid dynamics to come to a steady state before starting the plasma, and it's a pretty low Reynolds number flow. So we expect it to be relatively stable, but then we apply a high voltage pulse. So the high voltage pulse goes into an electrode that's on the inside of the tube now, and an ionization wave propagates to the end of the tube, out the end of the tube, and we see a hot spot form. This is the electron density and a high density region right near the powered electrode. And this produces very localized gas heating right at the end of this electrode, up to 800 K, but in a very small volume. And then as time passes, over several microseconds, that's allowed to expand, and a pressure wave propagates to the end of the tube and disturbs the density in this shear flow region where the helium is flowing quickly into the surrounding air. And it causes an instability. So a shear flow is prone to a Kelvin-Helmholtz instability. And we see oscillations in the velocities as well as in the amount of nitrogen that is diffusing in. So this is, you can think of it as the interface between the helium and the surrounding air is wiggling. And because it's a model, we can turn off the gas heating. And so we run the simulation without the gas heating. And this is actually an animation, but nothing's happening because we turned off the gas heating and that was the cause of the instability. And just to emphasize why this is important, we ran a simulation where the flow conditions are kind of crazy and launch an ionization wave into it. And the ionization wave really follows the region of highest helium density. So it prefers to propagate in the helium over the molecular gas where there's lots of vibrational energy losses. So towards the end of my PhD, we did a validation study of comparing with experiments for electron density measurements. And in order to do this in a more robust way, we put everything into a vacuum chamber so that all of the airflow and nothing would be affected by room air currents. We could control the composition of the gas, both in and around the jet, and used a jet that has a central tube for the main ionization wave, and then also a shroud so that you can flow a different gas composition around the main jet. And the plasma, something like this. And we put it in a vacuum chamber, applied a positive 6 kilovolt pulse, and put it in 200 torr of helium, which is not atmospheric pressure, lower. And that helps with both the modeling and the experiment. The modeling dynamics are a little bit faster, and there is a lower background for the electron density measurement. So a little higher sensitivity there. And we used a technique called laser collision-induced fluorescence to measure the electron density. So this uses an ultra-fast laser to measure time and spatially resolved electron densities. So this technique relies on the plasma generating the first excited state of helium, then uses a laser to excite to a higher excited state. And then if there are electrons around, they can cause transitions to these other nearby excited states. And we can take a ratio of the emission from those states of the laser-induced emission in order to indicate the electron density in the right conditions. This technique was developed by Ed Barnett for pure helium. And in this effort, we extended it to some mixtures. So then we were modeling this setup. And in the initial simulations, with a positive applied voltage, the ionization wave would barely propagate, much different than what we saw in the experiment. And this is because positive ionization waves are really sensitive to what's happening ahead of the ionization wave. So in the bottom case, we have an ionization wave that's coming from a negative electrode, and the electrons are being pushed forward ahead of the ionization wave. So you always have some kind of source of electrons out in front because they're coming from the bulk plasma. In the opposite case, where the plasma is coming from, or the ionization wave is coming from a positive electrode, all the electrons are getting sucked back into the bulk plasma. And so there needs to be some source of electrons out in front. And usually that is attributed to either something that's remaining from before, from previous pulses, or photons, some combination of those. And so in this case, we had included photon emission, radiation transport in the model, and ionization in the bulk gas, but we didn't include photoelectron emission from the inside of the tube. And that actually dominates over the bulk gas. And we also had made an incorrect assumption about which radiation lines are most important. It was assumed that in a lot of models that X-emitter emission was most important because it's not trapped, and that the line radiation would be trapped locally in the ionization wave. But really, when you look at it quantitatively, there is more relevant fluxes from the line radiation. So including those and including the photoelectron emission from the surface moved us from a central plasma to one that is more wall hugging, which is what we saw in the experiment, and towards more similar ionization wave propagation speeds. Now, once the ionization wave came out of the tube, the simulations on the right here are some of our initial attempts, where it says no electron Monte Carlo, no EMCS. And as the ionization wave approached the surface, it kind of stalled and hovered above the surface, which is the opposite of what we saw in the experiment. It really should accelerate towards the surface, which makes sense. The field enhancement in that region is very high. And so we had to include kinetic effects of the electrons that are coming off the surface due to photoelectron emission in order to capture this speed up and even just get the qualitative behavior of the ionization wave right. And so including those secondary electrons or those photoelectrons as particles kinetically allows us to better capture the ionization that occurs ahead of the ionization wave towards the surface. And then we also added, we did not want to compare just one set of conditions. So looking at the trends as we vary the conditions, in this case, we added a humid helium shroud. Ideally, you'd want to do air because that's what's representative of a real plasma jet in a real environment. But nitrogen is a little bit too much for the laser collision-induced fluorescence diagnostic. So we couldn't measure the electron density accurately if we included air. And we captured the ionization wave speed increases the presence of humid shroud. That's more, that's due to more photoionization as well as the lower ionization potential of water compared to helium. And we captured some of the basic trends. The plasma moves from being on axis to being more annular in both the experiment and the model, but there's still some significant differences. These are plotted on different scales. So in particular, the max density is higher in the model, and also the variation, which is on a log scale. So there is more variation in electron density in the model than what we see in the experiment. And so there's still some work to be done, but we're at least capturing the basic trends here. So I'm going to switch gears and away from plasma jets and talk about the activation of liquid droplets. So plasma treatment of liquids is often transport limited. Only the top surface, the top few microns of the surface gets exposure to the reactive species. They're diffusion limited. And so several studies have looked at plasma activation of aerosols because they're just higher surface area to volume ratio if you want to get high densities of reactive species. So these could be for things like electrospraying water for disinfecting surfaces or generating hydrogen peroxide. And in a system like this, we have to consider a lot of plasma chemistry. First, the electron impact reactions in the background air produce, this is just a small subset of what's generated, but it's the most important ones. So we get dissociation and excitation. And then at longer time scales, those reactive species react with each other and with the surrounding air and produce more stable and more complex species like nitric acid. And then all of those things can solvate in liquid water and undergo solvated reactions. And they often, the most excited states often react directly with water. So the blue dots are here. And the reactive oxygen species and reactive nitrogen species react with water, but also with each other to form some of the more stable and more larger molecules. And so to address the problem of plasma activated droplets, we used a global model in order to investigate these really complex reaction mechanisms and long time scales, many pulses. So we're able, because it's a global model, we're able to reach 500 pulses with 10 seconds of afterglow. And that's important for biological applications or applications where you may be plasma treating these droplets, but it takes a while before they reach a surface that you actually want to treat. And in the gas phase, we see that some of the most reactive species, like oxygen, are produced and then decay with every pulse, with every voltage pulse. And some of the more stable species, like ozone and hydrogen peroxide, H2, are accumulating from pulse to pulse. And some species, like OH, reach more of a pulse periodic equilibrium. And then all of those species can solvate in the liquid and produce reactive species there, but because it's diffusion limited, these tend to be on longer time scales. And what we found is there's really two limiting behaviors in the effect of droplet diameter in the system. So there's two types of molecules. Ozone is one that really prefers to be in the gas phase rather than in the liquid. And hydrogen peroxide really prefers to be in the liquid rather than the gas phase. And so for molecules like ozone, the density in the liquid ends up being very independent of the droplet diameter. So it saturates in every case. But for hydrogen peroxide, the density in the liquid can be very sensitive to droplet diameter. It's on a log scale. And that's because essentially you're diluting all of the hydrogen peroxide you produce goes into the droplets. And if you have a larger droplet volume, you're diluting it. So switching gears to another application of low temperature plasmas, single particle aerosol mass spectrometers is a type of mass spectrometer that's used to study aerosols, the composition of aerosols. And because it's single particle, that means that you get a mass spectrum of each individual particle rather than an ensemble average. And this can really help attribute different particles to different sources and have different compositions. In this case, this single particle aerosol mass spectrometer device, they have a mass spectrometer, but weren't sure what is causing ionization, what basic process is causing the ionization. And that makes this data really difficult to interpret quantitatively. And it also makes it very difficult to improve this device at all. Maybe you want to use a different laser, maybe there's a better approach, but you don't know without knowing what actually causes the ionization. So we looked at a global model of a pure spherical aluminum particle with a two temperature approach. So one temperature for electrons and one for gas, for the neutral gas. And what we found was that the main photon absorption mechanism was not exactly what we expected. So the closest transition, the closest photoexcitation transition is at 256 nanometers. And the laser in this case was 248 nanometers. And so that shouldn't be a resonant excitation, but in these conditions, you've got enough pressure broadening going from a very dense solid particle into the gas phase. There's enough pressure broadening initially that can raise this cross section by several orders of magnitude, and most of your photons that actually get deposited are through this direct photoexcitation reaction, rather than some of the other processes that we considered, photoionization or photoionization of excited states, multi-photon ionization, and previously inverse Bremsstrahlung radiation had been speculated to be very important in these conditions. However, it's several orders of magnitude lower than the main photon absorption reaction. And we were able to identify the primary ionization mechanisms. In this case, it is electron impact ionization of excited states. So not of the ground state, but when you have the photons excite to the Y2D state, then superelastic collisions can occur, and this actually heats the electrons. And there's enough excited states still around that you can get electron impact ionization of excited states. And this process is a couple orders of magnitude greater than any of the other processes that had been speculated. So even though there's a lot of approximations associated with the 0D model, we're able to give a lot of insights by saying, oh, these processes are several orders of magnitude higher than others, and very likely the main process occurring. And lastly, a validation of a high fidelity model for DC breakdown. And so most of what I talked about is fluid and global models. And here we're moving to a fully kinetic model. And the goal of this project was to have a very simple setup, almost as simple as you can imagine, with a DC electric field applied across a gap. So there's a lower electrode that's grounded, an upper electrode with a voltage applied to it, and just to measure the current as it breaks down. Well, it turns out that if you do that, the breakdown is very stochastic. Sometimes you have to wait many seconds for anything to happen. So adding a mesh electrode and shining a UV light through it is just enough to trigger the breakdown predictably and repeatably, so that it provides a meaningful comparison with the model. In this case, the UV diode was 256 nanometers, and that is less than the work function of platinum. So it shouldn't really be enough to kick off a bunch of electrons, but it turns out to be just enough to barely kick off a breakdown. We use a one-dimensional particle in cell direct simulation Monte Carlo model called LCIF. And direct simulation Monte Carlo is actually fully kinetic treatment of not only electrons and ions, but also neutrals. And in this case, photons were also treated as particles. So the radiation transport calculation is more rigorous than is typically done as well. This was simplified to 1D, and the helium was assumed to be completely pure in this case. And we included 12 excited states and 141 reactions of just helium. And we attempted to reduce the mechanism further, but found that actually we needed about that many states in order to get the current right. And calculated the current from the simulation using a method that includes displacement current from Shockley and Ramo. And with all of these, especially with the particle photons, we ran these simulations on several hundred processors for multiple weeks. And even though the UV diode is not, UV light isn't energetic enough to cause photoelectron emission, we assume that maybe there's some impurities in the surface that make it possible, but that the current is extremely low. So matching the variation in the current rise time, the experiment, gives us an estimate of emitting 1 electron about every 6 nanoseconds. So this is an extremely low current. And then when an initial electron is emitted, it avalanches across the gap. And so after 10 nanoseconds, 15 nanoseconds, it's traversing the gap and also causing ionization by the time it crosses the full gap. And then after that, the full plasma starts to develop. The density rises by several orders of magnitude and it starts carrying a more significant amount of current. And we can look at the cathode, the sources of current. And initially it's all displacement current from these electrons moving across the gap, but very little charge actually crossing the plane or hitting the surface of the cathode. And then secondary electron emission due to photons, the photoelectron emission from the cathode, starts to become significant. And it's not until later, after about 150 nanoseconds, that we actually start to get helium ions hitting the surface. And those cause their own secondary electron emission, ion-induced secondary electron emission. Now, this seems to match very well, but we also had to shift the experimental curve by 112 nanoseconds. So there's an additional delay in the experiment. So the value of the photoelectron yield, gamma photon here, is not well known because you can have a platinum surface, but once you stick it in a plasma, repeat the plasma many times, you don't really know what's on your surface anymore. And so we use the value of gamma photon to fit the slope of the initial rise in the current. So that's the most physical relationship to that quantity. And the ion-induced secondary electron yield is determines more like the maximum or the steady state current in the discharge. But once we do that, we still have this 112 nanosecond additional delay in the experiment. And we believe that those could be primarily due to two effects. One is 2D losses of photons. So in a 1D model, every photon hits one surface or the other surface. But in a real 2D experiment, some of them are lost radially, and we don't account for that. We also suspect that maybe the UV diode, instead of kicking an electron off the surface, it generates an electron in between the electrodes. So maybe there is a negative ion hanging out that can be ionized, and that's what gives us the first electron. That may explain some of that additional delay. So talked about a variety of things, but I hope I've impressed upon you that low temperature plasmas are very important in medicine, climate change, communication, all kinds of areas. And computational modeling of these plasmas can be used to identify very important pathways and inform design of plasma-based devices. And that some examples of that are that admixtures in plasma jets reduce the sensitivity to impurities that you might not be able to control well. And gas heating can be the root cause of some flow instabilities in plasma jets. And we've described the general behavior of solvation dynamics for different reactive species at long time scales in droplets. And talked about the importance of photoelectron emission from surfaces, especially for ionization waves that are directed from a positive voltage. And we found that resonant absorption can dominate in laser-produced plasmas for mass spectrometry, and highlighted ways that comparing with experiments is critical for improving models, and not just the numerics of the models, but the assumptions that go into them, which photons we consider, which secondary electron processes we consider. And high fidelity models are computationally costly even for a very simple case. And we need more to think differently and think about more hybrid approaches to help bridge the gap between the very high fidelity models and the fluid models that include more approximations. So with that, I'd be happy to take any questions.
For your fluid models, besides using ionization method, do you use any other computational methods to help reduce the simulation time?
So the fluid models were not massively parallel. Those were primarily serial. And the most important method for reducing the simulation time, especially in the fluid model, is an approach called time slicing, where where you kind of choose the timescales of different physics. So we actually don't solve Navier-Stokes equation at every plasma time step. We solve Navier-Stokes equations that have slower dynamics, solve the velocity flow field everywhere, and kind of hold it static while we update the plasma on nanosecond time scales, and then occasionally pop back, update Navier-Stokes, and then go back again. So there's coupling, but it doesn't have to be at every time step. So that's a really important method. The other very important method that's kind of on the idea of time slicing is dividing the simulation up into considering different sets of physics. So in the plasma jet simulations, I mentioned we solve the fluid to a steady state and then start the plasma simulation. So you're not solving for the electric fields all the time. But then also after you solve for the plasma dynamics, after a certain period, we're really just interested in the chemistry, and the fields and the charge species aren't interesting. Most things have recombined. And so we assume basically ambipolar diffusion instead of solving for the electric field in the afterglow period. So the more important speedups in the fluid models are physics-based assumptions rather than numerical or parallel.
I guess to develop on that, we can talk about it later. But what are some of the exact physical criteria before you do this? How do you determine which points to go to which?
So a lot of them are just explicitly specified, so like user input, and haven't gone more advanced than that. We also do updates to the Boltzmann solver periodically, so the EDF can slightly change as the gas composition changes. And yes, in these cases, those are all just more converged quantities. So you make sure you're updating it enough, but not more than you need to.
Any other questions?
So for the global model for the water droplets.
Mhm.
Maybe I missed it, so I apologize, but the actual like typically how you interpret it is basically just droplets going through like a homogeneous plasma.
Yeah, so it's a well-stirred droplet in a well-stirred plasma. But there is a diffusion length, which I didn't talk about. And so the diffusion length describes the characteristic loss rate or the fluxes to the droplet surface of the neutrals.
Okay. Yeah, that makes sense.
And then it's there are 500 pulses of a DBD, which is just an assumed power deposition, pretty much a power per unit volume, and then an afterglow after that, where things are still diffusing and reacting, but there's no power deposition.
Go check, see if there's any questions on it. No.
Can I have one general question regarding the presentation? Which one is much more expensive, the computational one or the experimental?
Expensive in dollars or time? Femtosecond lasers are expensive, so probably that. In terms of time, I think for that specific the laser collision induced fluorescence measurements, I was visiting Sandia for a semester to take those measurements and to take a full data set, not just one set of conditions. And I think the modeling took me about that long, but most of the modeling was running things and realizing that they don't match, and then questioning a lot of what we put into it in order to get them to match. Looking at potential problems with the mesh and detailed in the assumptions and time steps and things like that to try to identify where we were going wrong. So running the model once is not too bad, but getting the model right takes a lot of grind sometimes. Okay.
Talking about the mesh, how did you determine that for your ionization?
That's a good question. And there probably could be improvements in this area. We refine it a little bit and see if there is any differences. But I think the question of exactly how fine your mesh needs to be is less certain for fluid and hybrid models compared for ionization, compared to the particle and cell methods. There's been more theory applied to how fine do you actually need your mesh to be so that you can say that it's fine enough because you're resolving all of the mean-free paths and and sufficiently resolving the Debye length. So that's a more established, rigorous analysis.
Any questions? You got me hooked on the whole quantum computing thing. I never heard that. Where's plasmas used in quantum computing?
Just in depositing, actually making structures. So depositing thin films and making nanoparticles or whatever you need.
Okay, gotcha.
So the processing side, yeah.
Any other questions? Well, I'll take one more. You mentioned that there are over 500 types of reactions. How many of those actually matter? And how do you determine that they actually, some do matter and some don't matter?
Mhm.
Beyond the simulation, is it even feasible to go into an experiment and try to identify these? Or do we just have to kind of close our eyes and just hope that all of our cross sections, everything are, are accurate?
Yeah, that's a huge question because in a lot of these reaction mechanisms, some of the rates are not well known. So we try to include as much as we can. And even if we have to approximate rates, a lot of times that's better than assuming that the rates are zero, which is what happens if you leave them out. And so I'd love to get into more rigorous methods of reaction mechanism reduction. There's been some work in that area, but not a tremendous amount for plasmas. So I'd like to look more into like what they do in the combustion community for mechanism reduction, because I think there's a more rigorous analysis there and some things that we could leverage. But basically, the process in a lot of this is include as much as you possibly can and let the model tell you what's important. But even for the last set of simulations that I showed, we had to reduce it even in 1D just to be able to get the simulations to where they needed to be.
And the helium one, you said that they all matter.
So we had more. We reduced it to a point where we couldn't anymore.
Gotcha.
And
I guess
so
it's an
they-
infinite number, but yeah.
Yeah, so it was a larger mechanism. We reduced it down some, and I'm sure there are smarter ways to reduce it. We just reduced it from the top down. In terms of don't include as many excited states, as high of excited states. But we did not try every set, we didn't try knocking out specific species one by one.
Gotcha. Any more questions? Going once, going twice? Okay, well, thank you very much.